Hi everybody, my name is Cliff Burdick. I work at ViaSat. We're about 20 miles up the street. If any of you guys are looking for somewhere to work and you're interested in this stuff, let me know. Today I'm going to talk about a Topology-Aware Scheduler that we built for Kubernetes. And we'll go over some of the reasons behind why we built it in the first place, because that's a common question that we get. So on the agenda today, we're going to go over some terminology that we're going to be using throughout the presentation. And then what are the requirements for HPC and NFV applications? What does it mean to be topology aware as a scheduler? Some of the challenges that we hit when developing this type of application, or these types of software when we deployed it in Kubernetes. And then we'll introduce our new scheduler and some of the future work that we're looking at doing on it. So before we get there, there's some talks that are very, very similar to this one. I think if you're coming to this, you're probably interested in these ones. I updated the room numbers as well. 2 of these are directly after this talk at the exact same time, so you have to pick between one of those. But then there's 2 more tomorrow that are kind of along the same lines as this one. So first for terminology, HPC stands for high performance computing, and it usually refers to a dense server, a dense collection of servers that are performing really high speed calculations, usually across many servers. The most common use case is you have really dense GPU servers and you're fanning out a whole bunch of data back and forth between them to work on a problem. Network function virtualization was where you implement a network function in software, and usually it's at a fairly high rate, multiple gigabits per second. NUMA stands for non-uniform memory access, and this refers to how the processors access the memory in the system. RDMA is remote DMA. This is where you transfer data directly from the NIC to a GPU. It's not referring to any particular protocol here, just the act of doing that. And these applications typically need very high network throughput. So 40 to 100 gigabit per second interfaces is very common now with HPC and NFV applications. InfiniBand's another type of interface that's very common. And usually there's multiple interfaces. So instead of just the single interface, which Kubernetes limits you to, usually you'll have multiple data plane interfaces in addition to the main interface. They usually require low latency, so under 10 microsecond turnaround time for packet processing is pretty common. And to get those numbers, we usually use SmartNIC. So they have hardware offloads like checksum offloads, tunneling. Some of them have encryption and compression. And then last, there's the accelerator cards. So GPUs are probably the most common for Kubernetes because they have first-class support now. But you could have FPGAs, TPUs in the Google Compute or any other type of accelerator card you can imagine. So what's needed to do an HPC or NFV application? So user space networking, specifically using DPDK, is one of the main features of an NFV application, which we'll get into next. Isolated CPUs, so you don't want anyone else running on the same CPU as you. NUMA awareness for both memory and devices. So if you're accessing memory, you want to know that it's local memory and not remote memory. And similar to any device that's in your system, you want to make sure that you're taking the fastest path to the device. RDMA, which I mentioned, is when you transfer the data from the NIC directly to the other devices. And that's instead of going through the CPU, which is the normal path of taking data in from the NIC, going through the CPU and out to the accelerator card. And then last is huge pages. And huge pages are used in DPDK mostly because you don't want a lot of page misses when you're working with large memory sets. So DPDK uses anywhere from 2 megabytes to 1 gigabyte huge pages. And the key point between all of these features is that they require some level of topology awareness to implement any of these. So really briefly, DPDK, for those that don't know, is a user packet processing framework. One of the main features of it, and the reason why people use it, is it completely bypasses the kernel for efficiency. I wrote here most of the time because there are DPDK drivers that don't bypass the kernel, but it's much more common to use the ones that bypass the kernel. And you're giving up a lot by not going through the kernel, but the people who use DPDK typically don't need all the things that the kernel is doing to the packets. One of the main differences compared to normal Linux packet processing is DPDK is polling based. So you sit there and you have a core that's sitting there, or a thread that's sitting there on a core polling the NIC as fast as it can to see if packets are coming in, as opposed to being interrupted when packets come in. There's also dozens of poll mode drivers. These are what DPDK calls the drivers that are used with it. And the poll mode drivers are nice because they allow you to write an application using the DPDK API. And if you switch to a different type of hardware or a different network card, you should only have to switch the driver underneath it and not change any of your code. And usually that works, but if you're using some of the more sophisticated features in DPDK, you might not get one-to-one parity between manufacturers. But from a high level, it works pretty well. And then last, DPDK is not just for packet processing. It has a really high-performance NUMA-aware framework for things like inter-thread communication, so ring buffers, memory pools. The memory allocation algorithm is extremely efficient in crypto and compression as well that they can perform in hardware. And even if you haven't heard of DPDK, it's usually the foundation of many of the high-speed packet processing libraries out there. So if you use T-Rex by Cisco, there's another one by Juniper. They all use DPDK under the hood. So what does it mean to be topology aware? So in Kubernetes, from a simplistic point of view, this is what it looks like when a pod gets scheduled. It comes up to the API server. The scheduler sees that a pod is ready to be scheduled, finds some resources for the pod, and then schedules it to a node. So number two is really the part we are focusing on because that's the biggest problem. What does it actually mean to be a CPU core? What does it mean to be memory? Is it all the same amongst all your nodes? So for high performance computing, I mentioned huge pages earlier. So that's one of the applications where memory is not all the same. Some systems may not have huge pages turned on, some might have different size huge pages, and you really want to find what's appropriate for your application. So from a top level view, when you look at a single socket Xeon with hyperthreading off, it's fairly simple. You have, in this case, 20 cores. Each core has an L1 and L2 cache that it uses. And then there's a shared L3 cache for all the cores combined. And then below you have a DDR controller that has about 80 gigabytes per second going out to main memory. So when you're scheduling a pod on a processor like this, it's not too difficult. You can treat all the cores as mostly the same. They all go through the same memory controller, and they all share the same L3 cache, and they all have independent L1 and L2. But when you look at the much more common server processor, which is a dual Xeon processor, or a dual Xeon server with hyperthreading enabled, now not only you have two sockets, but you have hyperthreading on both of them, and the number of logical cores goes up to 40 in each processor. And the main difference there is that now you have two logical cores that are paired up with each of your lower level caches, L1 and L2, and then L3, which is still shared between all those cores on each of the processors. And the other difference here is that you have two DDR controllers now. Each of those can independently go out to DDR at about 80 gigabytes per second again. And now you have an interprocessor link, in Intel's case called the UPI or QPI, that runs at about 35 gigabytes per second. So this is, now you can start to see the problems where there's a scheduling issue where if you put an application on core 0 and then another application on core 20 on the processor on the left, you could have a lot of cache thrashing because they're not aware that they're on the same, they're sharing the same caches there. And even if it was your own application that was being placed on 0 and 20, your own application might have a situation where those cores don't share data, so you wouldn't want them sharing the L1 and L2 cache. And then similarly, if you have a thread that's on the left processor, you don't want to access memory on the right processor because that incurs more latency and more throughput penalties going through the UPI bus. And if you zoom out a little bit, now we're adding two GPUs and two NICs, which are each connected directly to the PCI bridge on the Xeon processor. It looks very similar to before, but now you have the PCI Express interface above that, where the GPU and the NIC can both hit the processor at about 100 gigabytes per second or 12.5 gigabytes per second. So this isn't too difficult, but now if you're using RDMA, you need to make sure that the NIC going to the GPU is on the same socket. You don't want it crossing the UPI socket. But in this case, there's still only two GPUs and two NICs, so it's not that high of a rate. Even at 100 gigabits per second, the UPI bus may be able to sustain that without having any contention. But if you look at the more common GPU servers, now you have 4 GPUs and 4 NICs, which two are bound to each processor through a PCIe switch. So now, in addition to having the two processors there and the link back to the processor, you have each of the CPUs each of the GPUs and the NICs going at about 100 gigabits per second back to a PCIe switch. But now there's only a single 100 gigabit per second link going back to the Xeon, which causes a bottleneck. So you could see just by this, if you needed to transfer the data all the way back to the processor and then back up to the GPU, you wouldn't be able to do it with more than one of the throughputs of one of those NICs if it's a 100 gig NIC. So you really have to be aware of the PCIe topology here, as well as things like RDMA. And then if you want to get even more complicated, this is an actual server from Supermicro where there's 16 GPUs and 16 NICs. So you have a total of 32 PCIe 3 16-lane links between the PCIe switches and the devices. And not just that, now you have a tiered PCIe switch topology where from the top level, you still have the 2 GPUs and 2 NICs plugged into each PCIe switch. But if you go down one level, you can still go back up to the other GPUs and NICs without going through the processor. But again, it's only one link. So you're bound by that 12.5 gigabyte per second link. And again, if you're transferring data from the left side of the processor to the right side, now there's a huge bottleneck because UPI is only doing 35 gigabytes per second roughly, and you have 32 times 12.5 gigabytes per second from the top. And from a network point of view, if you're assuming that you have pods that have different bandwidth requirements, some pods might want, for example, on the one on the bottom left, it needs 5 gigabits per second. The one in the middle might have 2 separate processing paths where one path needs about 25 gigabits per second, and then the other path needs 30 gigabits per second, and then you have yet another pod with 40 gigabit per second requirements. Now you want to place those potentially on multiple NICs, but you also want to place them in a smart way where you can have pods share a NIC. And in this case, this node has 3 data plane NICs that these 3 pods could share, but you obviously can't take the pod on the right that needs 40 gigabits per second and tie it to the NIC on the left, which is only a 10 gigabit NIC. So some of the challenges that we face when writing the scheduler were isolating CPU cores, CPU selection, and NIC interface sharing. So first I'll go over isolating CPU cores and how we solve that. So for isolating CPUs, what you're doing is you're trying to prevent unwanted processes from running on the same core that you have something running on. And the reason is that it prevents cache thrashing. If you have 2 things running on the same core and they're both hitting the cache a lot, then the cache is getting evicted quite a bit. And it also reduces the time slicing. And you can actually eliminate it too in Linux, where if your process is the only thing running on that core, then you don't need a time slice between any of the other processes. So one of the problems, though, is that kernel processors are a little trickier. So some kernel processes can't be moved at all. If you try to move them using any of the provisions in the kernel to move them, it won't do anything. Things like interrupts also need a special configuration. If you try to move the interrupt processes, they won't do anything, but you can do that on boot. So there's effectively 2 ways to handle isolating CPUs. So the first is to use ISIL CPUs, which is something that's been in Linux basically since the beginning. And this allows you to isolate CPUs on boot up. So it's a boot parameter that you set up in Grub, and you specify a list, like in the top right up there, where in this case, the first 2 cores of the first socket are not isolated, and the first 2 of the second socket are not isolated. So what that means is that all the processes that will come up from on boot that can be on the non-isolated cores will be moved there, but some of the kernel processes will still be on the isolated cores. And then when you want your application, yeah.
Is that threads too, or?
Threads and processes, yeah. And if you want your application to use the isolated cores, you would do something like task set or call schedule set affinity or any of the other ways you could do it. And you have to explicitly set it, because if you don't set your application to use those cores, it'll be forced back onto the red cores in this picture. The second way is CPU sets. So this is a more recent feature that was added in the kernel in about 2008. So these are nice because you can create and modify them after boot. And creating a CPU set doesn't actually do anything until you put processes into the CPU set to isolate them. So what it does is it creates a group of CPUs that are visible to any of the processes that are placed into that group. So in the example on the top, the group name is /systemd, which is a common one if you're running systemd. And then within that, there's 5 cores there that are not visible because you set them to not be visible in that group. So when a process is moved into that systemd group, it won't be able to see those cores on the system anymore. It can't use them. And you can move any number of processes that you want into that group. And the other nice thing is it's hierarchical. So in the bottom example, you have kubepods burstable, which is one that you get with Kubernetes, and then kubepods burstable / pod 1. So it's a nested group inside of the top level group. And when you have a nested group, the child groups have to inherit all the rules from the parent group. So in this case, there's 3 cores that were not visible in kubepods, and then 1 level down in the child, there's 6 cores not visible. And if you move a process into the parent, they won't see those 3 cores. If you move them into the child, they won't see all 6 cores. And as I mentioned earlier, Kubernetes uses this. So if you look on your system and go into the file system to look at which CPU sets are set up, you'll see those kubepods groups in there. But one of the things we found was it needs special care with ISIL CPUs, because when we brought up our systems with ISIL CPUs, even though most of the Kubernetes processes like kubeproxy and kubelet were kind of isolated, every once in a while you'd see a thread from those move over to the isolated cores from ISIL CPUs. So what we did was we solved it by making a daemon called ISIL CPU Set. And this is essentially a daemon that runs on startup, and it makes 2 groups on boot. One is called the isolated CPU set, and one's called the jailed CPU set. And the first thing it does is it moves all the tasks or processes that it can into the jailed CPU set. So anything that might have been on the isolated cores at that point will now be moved into the jailed set. And then if your pod wants to be moved into the isolated set, it communicates with this daemon to tell it that it wants to be in there, and then the daemon moves it to a CPU set that is allowed to go on the isolated cores. So what this does is it gives you extra guarantees. You have ISIL CPUs still in there, but now you have an extra set that is jailing off all the tasks that use CPU sets, and you can move any of your processes into the isolated CPU set that you want to. So the next thing we had challenges with was CPU selection. So with most applications, you don't really care about this. If you launch a normal pod that's not DPDK or doesn't require special CPU core handling, Linux will take care of that. It'll usually leave your application on the same core, or if that core gets overloaded by other tasks, it might move it to a different one. But when you're working with NUMA and PCIe aware topologies, you need better than that, because you're typically looking for very low latency. So you not only do you not want your processes moving around, but you want to pick a specific core that you know is isolated from all the other processes on your system. And in addition to that, DPDK requires that you pass in the list of physical cores to it when it's initialized. So you have to know it when you're initializing DPDK. So the CPU manager for Kubernetes that comes with the stock version will do this on a best effort basis, but it won't do it by physical core numbers. So it will give you some level of isolation, but it won't tell you what the isolated cores are in your pod. And in addition to that, it's not hyperthreading aware. So if you care about the difference between hyperthreaded cores and non-hyperthreaded cores, it's not going to know that. It just treats them all as cores. And the last thing we had to face was sharing a NIC or sharing an interface. So again, this isn't an issue without DPDK, because if you're using standard CNI plugins like Calico or Flannel, they all go through the Linux kernel and they set up things like IP tables or IPVS to route packets appropriately. But when you're working with DPDK, you're bypassing the kernel entirely. So Linux and IP tables won't even see the packets. And also kubeproxy, which was previously there to steer the packets for services, won't see the packets either. And also, if you're using DPDK, you want to share the interfaces without losing efficiency. Otherwise, you wouldn't be using DPDK. So we looked at 3 different methods for doing this. The first was a virtual switch. So with a virtual switch, all the pods will communicate from their network namespace to the virtual switch over some interface, which then hits the NIC. And 2 of the most common interfaces are vhost user, VirtIO user, or memif. So some of the virtual switches out there, if you're not familiar, are OVS, DPDK, OVS, VPP is another one, and there's probably more I'm missing. So the nice thing about this is you have an external controller that programs a switch. So you don't actually have to have a switch that knows about Kubernetes to begin with, but you can have a controller that knows about the Kubernetes network policies and things like that and program it after it's started up. The other nice thing is it's fairly flexible because it's platform agnostic. You can use a lot of these virtual switches between VMs and containers, and they don't care which one they're running on. But the problem is they can be inefficient. So you have that extra interface there that you're going through, and depending on which one you use, it can be extremely inefficient, like vhost user, or it could be somewhat inefficient, like memif. They're always going to have some level of packet copies before it gets to the NIC. But the real problem for us was it doesn't have RDMA support, and we really needed that. So if you're bypassing the kernel entirely, then the vSwitch wouldn't actually see the packets. So the next one we looked at was host device. Host device is a really simple CNI plugin that's in the upstream CNI repo that basically just assigns the entire device into a pod. And so once the pod consumes the device, no other pods can use that device, and the kernel actually won't see the device either, or the root namespace won't see the device either. So it's nice because you can add multiple queues to a device, and you can have your pod use multiple queues. But if you don't have a lot of NICs in your system and you're trying to put more pods than NICs, this isn't really practical. And the last one we looked at was SRIOV. So with SRIOV, each pod gets one or more virtual functions on the NIC, which is a concept in the hardware of the NIC. And each of those virtual functions has a unique MAC address. And with most modern NICs, it has more virtual functions than you could fit pods on a node. So it's not uncommon to see 512 virtual functions or 1,024. And it's also very little overhead because your pod is sending directly to the NIC. And another nice feature on these is because it's in the NIC itself, you can actually set up some of the NICs to do kind of a switching interface or a bridging interface on the NIC. So you can have local traffic from the same node without going out to the switch. It could be bridged back into another pod. And SRIOV has mature Kubernetes support. So there's been a CNI plugin for a long time, but there's also now a device plugin for the last year or so. But the only downside that we found is that it may not have the same flow programming. So if you need to use some of the sophisticated flow programming features in the NICs, if you're using SRIOV, some of the virtual functions may not allow you to use certain flow features. So with all that said, now we're going to talk about our Topology-Aware Scheduler and why we did it. So from a high level, the NHD scheduler is topology-aware, and that means PCIe, NUMA, hyperthreading, GPUs, data plane NICs, and I'm differentiating that from control plane NICs or the standard Kubernetes NICs because this is when you're using multiple NICs. The CPU and GPU architecture as well, so if you have different types of GPUs or different types of CPUs in your cluster, it would know about those. And then helper versus data path cores. So in most data path applications, you have some cores that are doing things like management or they're listening to gRPC requests, and you don't want them to be on isolated cores necessarily, so you want to treat them as more fungible cores. It's written in Python 3, and it has a gRPC interface for retrieving cluster statistics. So the main algorithm for the scheduler is it watches for pods to show up that are looking to be scheduled by this particular scheduler, translates the configuration from the pod into a common format that it uses to make a topology structure, matches the pod to the node, translates back to the pod's configuration structure, and then binds that to the node. And the reason why we do the config translation is because the scheduler has a concept of a generic topology structure, and every application has their own way of configuring it. So the config translation takes your specific application's configuration and translates it into this generic format that it can use to schedule. So the matcher step is the most important one because that's the one that actually does the packing. So it tries to find the best possible node to place your workload. But it also tries to pack as many on there without being inefficient. So you wouldn't want to just put as many pods on a node as you can and then overload the node so that you're causing jitter and latency that you don't want. And also, it can't predict the future. So it would be nice to, if you knew 5 minutes of incoming pods and what their requirements are, and then you could schedule it and do better bin packing. But usually in Kubernetes, you want it, if you're deploying a pod, you want it to be deployed as soon as possible. So the first stage that it does is it filters the pod resources, which are currently just huge pages, and later we might add them once Kubernetes has support for more resources. And then it does a NUMA and PCIe filter on both the CPU and the devices. And then it intersects all of those. So it'll look at your GPU, your NIC, and your CPU requirements, find which PCIe switches and NUMA nodes are available, and then intersect those to find which ones you can be placed on. So this is a pretty common picture of a data plane application where at the top you have two hyper-threaded helper cores, which are the ones I was talking about earlier that are for kind of management type stuff. And then in this case, your pod has two processing groups. So these are two independent data paths that might have no relation to each other, but you want them in the same pod. So on the top case, the dark blue boxes are the non-hyper-threaded CPU cores that you require. And then in that case, you need 3 GPUs as well, which are the dark red circles. And the bottom processing group in this case is using hyper-threaded cores. And then on the left side is the receive networking requirements. So you have 15 gigabits per second and 80 gigabits per second in those. And on the right side is the transmit networking requirements. So if we look at how we place this onto a node, now if we take one of those processing groups from the bottom and try to place it on this node, in this particular case, it's asking for 7 non-hyper-threaded cores, which are the dark blue down there, 3 GPUs, 15 gigabits per second on the receive, and 50 gigabits per second on the transmit. So if we look at, in this case, there's only 2 servers, so it's a very simplified view. But the 2 servers are broken up into 2 NUMA nodes. So on the left side, the left green box is NUMA node 0 on the first server, and the right one is NUMA node 1 on the first server, and similar on the second server. So the first thing it'll do is it'll look at how many servers or how many NUMA nodes can suit the CPU requirements. So in this case, it's asking for 7 CPUs, so we're looking for basically 7 white boxes here. And you can see both NUMA node 1 on server 1 and NUMA node 0 on server 2 can meet that requirement. They both have 7 cores that they can assign. But then we're also asking for 3 GPU cores. And now the second NUMA node on the first server doesn't have that many GPUs free, so it's not allowed to schedule there. So it'll put it on the second server in NUMA node 0 because also the networking requirements are met on the bottom there. But now when you turn hyperthreading on, it gets a little more difficult because now the cores are broken up into 2 separate groups. There's 2 logical groups of the top and bottom there. So logical core 0 would be paired with logical core 6, 1 with 7, and so on. And so now when it's scheduling, it has to be aware of hyperthreading. So in this case, we're asking for 5 hyperthreaded cores and 2 GPUs. So if you look down at the bottom and you look at which ones have 2 GPUs free, both NUMA nodes on the first server have that free, but only NUMA node 0 on the second server has that free. And now we look at the cores that it's requesting. Now we're asking for 5 hyperthreaded cores. So it looks like NUMA node 1 on server 1 has that, as well as NUMA node 0 on server 2. But actually it won't work because server 1 on NUMA node 1 on server 1 can't be scheduled to in this case, because if you look at the hyperthreaded pairs, which are 2, 8, 1, 7, 0, 6, and so on, the sibling core in each of those cases is already used. And you don't place a workload on somewhere that already has a pod scheduled on a sibling core, because now you have a pod that's not yours that would be sharing that sibling core and you can't control it. So in this case, the only place it could put it is on NUMA node 0 on server 2, because even though it shows 4 or 8 hyperthreaded cores unused, these would still take up the 2 siblings. So in this case, it would put it on 2, 8, 5, 11, and maybe 1 at the top, and it would use those 5 hyperthreaded cores. And so the last thing it does is it binds the pod to the node. So this is exactly how the Kubernetes scheduler does it. It issues a bind command through the API server that basically sets the node parameter on the pod to the node that we want it bound to. And then it makes native Kubernetes events that will tell it that it's binding. So if you look at kubectl get events, you will see something like at the bottom there showing that it's scheduling onto that node. So one of the things that comes up is why not use the upstream Topology Manager? So this was introduced in 1.16, the latest version of Kubernetes, as an alpha feature. So the Topology Manager is a little bit different in that it gets topology hints from hint providers to map devices to other resources. So one example of that is you might have an Nvidia GPU device plugin that gives you a hint about which NUMA node it's on, and then the Topology Manager can then bind that particular GPU to a NUMA node. So, but the biggest difference is this is not part of the Kubernetes scheduler. It's part of kubelet that runs on each node. So it's possible for your workload to be scheduled to a node by the scheduler and then kicked off by a kubelet because the resources aren't matching the NUMA requirements that you wanted. But it looks like they're also adding PCIe awareness soon. So our hope is that the upstream Topology Manager can add the same features that we've been working on so that we don't actually have to use our scheduler anymore. So some future work, number one was open source. It was going through legal up until yesterday, so we were able to open source it. So that's the link there if you want to check it out. We're also working on getting the containers pushed to a public registry. Right now it's only internal. So if you do go get the code, you can build it, but it will not push anywhere right now. Pretty soon it will probably be on Docker Hub or maybe Quay. And then we're also looking at Intel's resource directory technology, which is effectively a whole suite of things that you could do on a CPU to manage contention and manage resources. So one of the things that's most interesting for our scheduler is you can manage the cache and memory bandwidth allocations. So as an example, if you had a pod that you know might use 2 megabytes of L3 cache, you could make that a resource going into the pod's resource spec so that when the scheduler sees it, it would also use that in its decision to place it on a node. So if you had another pod that, for example, was going to use the entire L3 cache, then you would only place that pod on a node that had no other pods running on it. And it also allows you to segregate the cache. So with that technology, you can make a specific pod assign certain cache lines or certain cache ways so that no other pods can use that and you avoid the noisy neighbor problem. We're also looking at some speed improvements. Right now, it's a little slow. It's definitely not as fast as the upstream scheduler. We didn't intend it to be that fast, but it's definitely slower than it could be. But right now, we're running it on about 30 nodes, and it's fast enough for that. But at a higher scale with hundreds or thousands of nodes, it would be far too slow to be used there. Another thing we've looked at is NVLink topology. So if you're familiar with GPU servers, the topology for the inter-GPU connections can vary from server to server. Some of them have full mesh, some of them don't. Some of them have more lanes going to certain GPUs than others. So if we had that awareness as well, we could build that into the scheduler. And then last was to delete the project. So we don't feel like we want to maintain a scheduler from this point on. So the only reason we have it is because the current scheduler doesn't meet our needs. But if the Kubernetes community starts to add in some of these features later, we won't have to use the scheduler anymore. So last, I just wanted to say thanks to some people at ViaSat, Tim, Federico, and the rest of our signal processing team. Peter's our Kubernetes guy. And then some of the other people at this conference, Duffy, Luis, and Doug, that answered a lot of the questions getting to this point. My wife and kids, and Intel and Red Hat, mostly because they've done a ton of work in this area that we're leveraging. So for example, the node feature discovery plugin that Intel, I think, originally made, we're using that heavily to make decisions on how to schedule. And that's it. Any questions? Yep. Nvidia.
So that you actually...
the multiprocess?
Exactly.
Yeah, so yeah, that wouldn't be hard to do. We have not had a need to share GPUs across pods right now because if you go back to that one server that has either 8 GPUs or 16 GPUs, usually our pods, we wouldn't need to share those across many more pods than that because the type of CPU and networking workloads that we have wouldn't allow for that many pods on that machine anyways. So we haven't had a need for that, but I know that people do that. Although once you start doing multi-process on GPU, you're starting to ask for more latency and jitter than you would without that. So it can be done, but if you're going for the absolute lowest latency and jitter, you probably don't want someone else running on the GPU that you don't know what they're doing. I believe the latest NVIDIA GPUs, the V100 at least, has more segregation as to more fine-tuned granularity as to breaking up resources on the GPU, but I haven't tried it yet. Yep.
For the market information, where is it stored? How does the scheduler get the information on the server?
Where is what stored? Sorry.
For the market information.
Oh. So yeah, so right now we have it in a config map. So when a pod comes up, in our particular case, a pod comes up and it has a config map, which is the configuration for the pod. And that config map is what we mangle basically to assign physical resources. So the config map might have something like you need 2 logical CPUs and 2 GPUs. And then the scheduler goes and modifies the config map and puts the physical resources in there so that when the pod launches, it takes in the config map and it has all the physical resources that it needs. Yeah, so we're using the node feature discovery tool from, I think it's in the incubator program now. That's what reports all the properties of the node. And I forgot to mention, we did make some hooks onto the NFD, the node feature discovery tool. So things like ISIL CPUs weren't reported by that originally. And it allows user hooks, basically your own binary, to report more things about the node. So in addition to the default node feature discovery, we have a couple more hooks in there that are used by this that report things like SRIOV, the number of virtual functions on the card, the speed of the network interface, because some people have heterogeneous network interfaces in the node. So all the node information is reported by node feature discovery. Sorry, which has to be? No, we didn't touch any Kubernetes code. So the scheduler, since Kubernetes allows custom schedulers by just setting the scheduler name field of the pod properties, the default scheduler ignores anything that doesn't have that has any field other than the default scheduler in there. And then it's up to your own scheduler to watch for those pods. So we didn't have to modify kubelet or any of Kubernetes at all for this to work. So this is effectively a pod that sits in your cluster, just not like the scheduler, but it'll sit there running as a normal pod that's a replica set that when another pod comes online and it has this particular scheduler name in the scheduler field, then that pod watches for it and it assigns it to a node instead of the default scheduler. And what that also means is you can have both the default scheduler and the scheduler running at the same time. So if you have other people that don't care about these type of things, they could use the default scheduler and go to the nodes that are scheduled by the default scheduler. Yeah, so typically the way that we do it is any node that is going to be used for high performance stuff will be tainted for this particular scheduler, and the default scheduler won't use it. And then all the other nodes that are not used for that type of stuff will not have the taint on it, and they'll use those nodes. Yep.
What are the technical challenges of using something like Slurm as the Kubernetes scheduler? Is that possible?
So I don't know a whole lot about Slurm, so I can't really comment on that. The reason why we did this is we had quite a bit of runtime on Kubernetes, and we were really happy with things like the deployment time and the stability. And since custom schedulers were something that we could do without upstreaming anything, it was just something that we happened to do, and we're pretty happy with it. So we haven't really had any major issues. We did see a difference too. I mean, before you do things like isolating CPUs, before things like that daemon that moved them to the isolated set, we were seeing stalls of like 1 millisecond, which doesn't sound like a lot, but when you're doing real-time applications, it's a lot. And those go away when you do those kind of things. Yep.
So you're using ISIL CPUs and CPU sets?
Yes.
You use ISIL CPUs as well. Can you not migrate enough onto the JL?
Yeah, so the question is, are we using ISIL CPUs and CPU sets? The answer is yes, and the reason, and this may not be needed, but I believe that the kernel itself will pay attention to ISIL CPUs for the most part. So if you set ISIL CPUs, most of the kernel threads that can be moved will be moved right away. CPU sets, what we found was a lot of the things wouldn't be moved. They would be in the root CPU set, which is wide open. And so a lot of the kernel threads were still running on the isolated CPU set. So we had to force them off with CPU sets. So it was basically combining those two. And we looked in the kernel documentation. There's not a lot about how those two interact together. It seemed like ISIL CPU is just a legacy thing, and if you can avoid using it, you should. But using CPU sets alone didn't cut it for us. There were certain things we couldn't move by using just CPU sets. If you have any more information about that, I'd love to talk about it. Okay. And by the way, I have heard other people solving that problem differently. This is just the way that we happen to do it because we didn't know that they had solved it differently until after we already did. So, yeah.
How do you specify the CPU core selection and versus GPU selection in your scheduler so that Kubernetes can recognize it?
So the question is, how do you specify the CPU cores and the GPUs so that kubelet will recognize it? So in our case, kubelet doesn't care. So when you start up a pod from this scheduler, the pod is allowed to see all the cores, but it's only using the ones that were mapped into its configuration. So if your configuration says you're assigned 456, the pod is going to affine itself to 456 and device 1 for GPU, for example. So it's not the best way to do it because you could have a rogue pod that just starts using other ones, and that's not ideal. But right now we haven't really done any multi-tenancy with kind of bad actors where we had faced that problem. But kubelet doesn't need to know about the cores. So the cores are in the config map, and the pod starts up, reads the config map, and knows which cores it belongs to, or which cores it needs to use. Yeah. And the reason why we did that is we had a legacy application that had a config map already where we assigned physical resources. And as the project grew, that was really difficult to have everybody assign physical resources that weren't hitting someone else, especially on the network side. And so what this allowed you to do was not specify any physical resources and have it just populated for you by the scheduler. Yep, sorry.
Does it work on PowerPC architectures?
Yeah, the question is, will it work on PowerPC? I don't see any reason why it wouldn't. So you don't have to use GPUs, for example, even though they will work on PowerPC. The hyperthreading, I think on PowerPC has like 8 threads per core or something like that. So that should work still. I haven't tried it. I don't have a PowerPC to try on. But if it doesn't work on PowerPC, it would be a small change, I think. Any other questions? Yep.
You're using a daemon to report themselves to request the course that they're going to be advised to. Why a daemon and not just have a pod write its own bits into the CPU sets directly? Is it doing something else other than...
Oh, so your question is, why doesn't the pod move itself to the right CPU set?
Is the daemon doing something more than just taking a bit and writing it into SysFS?
That's all it's doing. Yeah, and I'm trying to remember why we did that. I think the reason was basically the PID inside of the container is different. I know you can set the host PID to have the host PID outside of it, but then it becomes more of a security issue because now you have to expose more things on the host to the pod to move itself. I don't remember if that was the exact reason we did it. I'd have to think about it more, but yeah, that's a good question. Yep. Yeah, so the problem we found with the Nvidia device plugin is it doesn't allow you to select a device. It gives you a random device that's on the machine. And that's not good enough for the reason I explained. So the pod itself has the physical device ID, and you no longer need the device plugin anymore because it's not using the consumable resource from the pod spec anymore. It's using just the device ID, and CUDA visible devices, the environment variable, is basically wide open. You can see all the devices. It would be nice if the device plugin allowed you to specify the exact device that you wanted, but that's not the case right now. Yeah.
But core is a user and code. What do you mean by core? You change the application code to that?
Sorry, I'm getting a lot of noise from out there.
So yeah, I mean, core is the user and code.
Yeah.
You change the application code to do all this stuff. I mean, to select which GPU.
So in our particular case, we already had an application that did that. We had an application that had a config file with physical resources in it that we would hand edit and then start up the pod, and that was cumbersome. So that takes the place of this. So if you didn't have our application, you were coming in with a different application, you would have your own config format that had basically placeholders for all those physical resources that you could tie back into your application and let it assign them and then move them back into your application. Thanks, that's a lot better. Yeah, the application has to do the same thing, but when you're using DPDK, that's the first thing you do when you initialize DPDK is pass the list of physical cores. So you have to know that anyways. You have to know your list of physical cores. So yeah, the pod has to do that, but instead of maybe having a static list of physical cores, you'll have one that's passed in from outside. Any more questions? Yep. So we use DCGMI to do health checks in the background. That is currently not fed back to this, but that's something we should do in the future. Yeah, the question was, do we do any GPU health checks? So if a GPU dies, you don't want to schedule to it anymore. So while we do that on the side, it's not fed back to the scheduler currently. And that's kind of one of the downsides of not using the device plugin is it does do the health checks for you, and it'll get rid of it. Any more questions? Yep.
Do pods need expanded privileges on the node to be able to input the resources themselves?
So the question is, do the pods need special privileges to pick the resources themselves? I don't think so. I don't think we're running with any special privileges. I'd have to check. I don't think we do, though. Originally, we were running with host networking, but we've moved away from that, and this works without host networking because I was presenting a whole bunch of other problems. But I can't think of anything else that's required. The container, I'd have to check. I forget. Any more questions? No? All right, thank you.